Thank you.
Thank you. This is actually not a ULDM or dark matter talk. It's essentially a publicity talk for Indian pulsar timing array. Just want people to know that we are working on these things and would like youngsters to join and all that. So okay, so again, you know all these things, but I just want to repeat it. That IPTA effort should be critical implication for beyond standard matter scenarios for both cosmology and particle physics, and they also have implication for dark matter scenarios. And since Anish was working on some of those, I thought I will kind of flash something, and I will give a very specific example using a supermassive binary black hole candidate. But again, the things are going to change in a decade's time, especially when we have, SK era pulsar timing array, where we are going to see not only just a background of nanohertz gravitational wave, but we will have individual supermassive binary black hole, and they will require us to kind of connect the Earth and pulsar term, which are thousands of years apart. So if there are, other exotic scenarios, they can actually change the dynamics. So this is essentially what I'm going to talk about. So that's what I've said, nano to hectohertz gravitational wave. I'm most likely also coming from the really low frequency gravitational wave that Subhendra talked about by 2050. I was just focusing on astrophysical things for the time being. He talked about cosmological. So, and I told you that even the lunar gravitational observatory may be out there, and there are already money given for preliminary studies. This is just an email from Karan Jani, and this is an exciting possibility. You can see that you can test lambda CDM and general relativity up to something like a redshift of 350 and things like that. It's a fascinating possibility. So, but the point here is that, this is Crab Nebula. The guy, this was the guest star of 1054, and it took a millennium to get this picture in various wavelengths in electromagnetic, using electromagnetic observatories. In the case of gravitational wave, that may not be the case. Within 50 years, we will have multiple gravitational wave windows operational and making discoveries. And then we are, and Subhendra talked about the cosmic microwave background, thanks to these three fantastic experiments for the last 30 years. And we also figured out that, they are gamma ray bursts. So in gravitational wave astronomy, we are finding something very similar. This is essentially transient events that LIGO is seeing, and we are getting a glimpse of the gravitational wave background in the PTA. And so that's essentially because of the PTA scenario. And of course, we have supermassive binary black hole at candidates. Again, so if you can look at omega square r cube is GM and use the quadrupolar formula for the amplitude, you can see that if you have binary black holes at a total mass around 10 billion or something like that, at separations of over 200 GM by C square, you should see things in the PTA band. We talked about that in the morning. I'm just repeating that for the. And if you are going to see individual supermassive black hole, I just showed in the morning that both the Earth and the millisecond pulsar terms will be important. They are essentially one arm of an interferometer, the galactic scale, and this is the kind of signals we are thinking. This is the characteristic strain and the frequency. You can see that there are a background because there are too many supermassive binary black hole in every frequency bin, and then eventually in by early next decade, we will start seeing this, kind of extra power in some of the frequency bins due to individual supermassive binary black hole in the foreground. And then we can even hope to see something called burst with memory. You can see that if a supermassive binary black hole merges, kind of scenario we are talking about LISA, it actually created nonlinear memory. That's the signal I've been talking about here. We can have other possibilities too, and exotic scenarios like cosmic strings and all that. So that's the kind of landscape we would love to explore, especially with the square kilometer array and FAST and many other telescopes. So I showed you this in the morning. So 3 types of sources are possible. An International Pulsar Timing Array. And the reason why I'm giving the talk is that Indian Pulsar Timing Array is an integral part of this. And we actually have used our own radio telescope. So we provide data, algorithms, and theoretical construct for so-called the 3P plus efforts. And we are also combining our data with other observatories for so-called IPTA DR3 efforts that's ongoing for the time being. And you can see that recently, even FAST, the CPTA is joining us. So that's a fantastic news for us. So we will have NANO-Grav, we will have the EPTA, we have the MeerKAT PTA, and we have in PTA and FAST as well as the PARCS, all are combining our resources together. The process is already on. There will be around 120 millisecond pulsar data, and we hope to get this phi sigma detection of the HD correlation that I'm sure that Mohanty talked about and all that. And we will also look for individual supermassive binary black hole using sophisticated expression for the PTA responses. Some of our kids are active on that. These are the co-leads, Aman, Shubhajit, Abhimanyu, Loki. Few more are going to do all that. So why this is so exciting is this, especially when the SKA becomes operational. You can see that this is a kind of the energy, it's a dimensionless quantity. It's essentially the energy density in gravitational waves divided by the energy density needed to close the universe, and it's the frequency. So you can see that this is LIGO domain, this is LISA domain, and this is the PTA domain with SKA. You can see that you get an improvement when the full SKA is operational, factor of 1 million. That's very unusual in astrophysics and astronomy. So that kind of sensitivity are expected, and so that's what there are lots of excitements, and obviously many of the youngsters will be in a very good kind of sport to do many of those. We are all getting old, so and this will have important implication for dark matter and also the phase transition and all that. That's because of that kind of sensitivity. Okay, so that's just want to give that message loud and clear. And more importantly, SK is under construction. And so this is just from a paper I extracted. This is a paper by D. Lee, who's in charge of FAST, and his student, and they are talking about the sensitivity of LISA, SKA when it's operational for 10 years. You can see that you'll see a background, but there are many individual supermassive binary black hole candidates we suspect from electromagnetic observation. And one of the guy there is that OJ287, and I will talk about that specifically to say that it can actually be used to constrain dark matter scenario. That's essentially my talk. And so that's the that's D there. Okay, so what's this OJ287? So this is not a theoretical physics talk, it's a kind of a more popular semi. So this is a blazar. It's an active galactic nuclei in our ecliptic. Okay, it's very close to the ecliptic, and we were looking at this guy unintentionally for the last 120 years because this is a star, a bright star. It varies rapidly. So we have a scenario where we argue that this blazar is actually hosting a supermassive binary black hole that's actually emitting, in our description, nanohertz gravitational wave. That's essentially because of multi-band electromagnetic observations. How do we do that? Well, this is very unique in the sense that this is the optical light curve. Magnitude is essentially the luminosity as a function of time. You can see that there were data points here, and you can see that when you kind of zoom on some of these peaks, they seem to be, associated with, certain flares, in the sense that the magnitude of the guy kind of rapidly varies. And these things happen over a few weeks. And these things last for a year. And that's the reason the background I'm talking about. So it's a very bright blazar. You only need a 50 centimeter mirror to actually see this. And so again, 120 plus year light curve is known. And we can roughly see this kind of flare. And remember, so that's what I'm saying, quasi-periodic double peak high brightness flares. Remember, I kind of mentioned about something called quasi-periodic eruptions. People are picking up these days. And essentially, that scenario is sort of influenced by what Maury and others worked out earlier. So what we argue is that there's a supermassive black hole here with an accretion disk, and there's a companion which comes and plunges through the accretion disk. So it's a binary, and then when it plunges through the accretion disk, you get flares. So it's fairly similar to what this QPE people are seeing these days, with less data points and all that. So we have been kind of playing around with this. The good thing about it is that we can actually track that secondary binary black hole trajectory using so-called post-Newtonian approximation to general relativity. That's what I still work on. And it has certain complicated structure. These are the conservative terms that causes the orbit to precess. These are because of the emission due to gravitational wave. These are the spin effects. So we can actually predict, we can pull in all that. We have already historical data points for the flares. So we can actually predict that in this model. You can see there's a very short binary. You can see that the orbital times, length scales are something like 20,000 AU. Yes. It's there, but you don't have to really worry about it, because those I can show comes at, in the trajectory comes at something called 5 p.m., so I can ignore it. Yes, but they do play a critical role. We can see that in the scenario, the black hole trajectory comes and hits the binary, the disk here, but the flare will come out much later. And that's the interaction, because, these things cannot happen instantaneously. You essentially kick out a spherical ball of material which has to be optically thin to get the flare out, and things like the Bremsstrahlung radiation. So you can see that, and then there were, prediction around 2007, there is one on 2015, and there's this is the model. And so game is that if you do this kind of model, you have to go and, observe. And till 2018, we were able to predict and observe 2005 flare, 2007 flare, 2015 flare. This we call Einstein centenary flare. And in 2019, one we call as the Eddington, flare, just to kind of 100 years. And so we actually made a paper on that, and then said that we predicted that the flare should happen in July 31st, 2019. You don't do that kind of prediction for blazars, because they get flares all the time. You make a fool of yourself. And when we wrote this paper, the referee objected, saying that, well, you guys are smart, because during July you can't observe OJ287 because it's an ecliptic. It comes too close to the sun. So no telescope will look at it. The solar angle was some 6 degrees or something like that. Fortunately for us, the Spitzer space telescope was, it was getting warm and it was drifting away from Earth. So we wrote a proposal saying that why don't we use Spitzer, which was drifting away from Earth, something like 3 million kilometers away. So it has a vantage point to see objects close to the sun. So we wrote a proposal saying predicted Eddington flare and first observation test of black hole binary. It doesn't matter. So this was, they said Spitzer was not meant for any of this. Anyway, you just want to see a blazar, fine, go and do it. We got time. And so this is I don't know whether you are familiar with, I'm a big fan of this movie. So it says, small chance of success, what are we waiting for? Anyway, failures are guaranteed if you try to predict flares from blazars. So then we essentially did that, and this was the data. You can see that that's the, so we actually predicted that the flare should look like what we saw in 2007. There's an argument for that. So you can see that that's the theoretical curve, and these are the data points. And so it gives a very nice argument that there may be a supermassive binary black hole in OJ287, and even NASA was kind enough to give us very nice publicity. Let me just play that for a second. So I will tell you why we are excited about it. So this is, it will give me a second and it should play. In case you don't follow what we are doing, it just gives you that. Yeah, so you can see that this is the cartoon, which based on actually post-Newtonian trajectories, you can see that that's the secondary black hole giving that flare, and you can see that they are not going to be periodic because of the precession and all that. Anyway, so that's, so if you want to know how the trajectories look, this is the prediction. We can stop that. You can see this is essentially what, and whenever that touches, we get the flare and all that. Anyway, so it's a simplified model. We have the data, and it came. So again, we kind of fool around saying that Spitzer actually did a test for GR. They're very happy about it. Okay. So why this is exciting? Well, so this is a blazar, and the blazar means the jet is, it's a active galactic nuclei with the jet directly onto you. So we can actually measure what will happen to that position of the jet projected onto the plane. And so, this has been predicted by us, and this is now being kind of used by EHT, that's Event Horizon Telescope. So we have a prediction how the jet will wiggle in our supermassive binary black hole model. This has been done by EHT plus something called GMVA. Anyway, so those are, but interestingly said, this guy will emit nanohertz gravitational wave in our model. SKA should be able to pick it up. So we are developing all these algorithms to kind of search for such events. Yes. So this is fairly extreme. In the scenario, it's around 150 million. Okay. And but again, we are, whenever we have opportunity to test with the observation, we do that. So the EHT is the next step and all that. Anyway, so why this is exciting? Because then there was this paper last year which appeared in Abjay Letters saying that a robust evidence for dark matter density spike around the supermassive black hole, primary black hole. They said that if there are dark matter that should get redistribute near the supermassive black hole, especially the primary, it can give you density spikes, which give you a dynamical friction, and that will affect your binary orbit. You should have seen it, and they claim that our analysis should have seen that. So we kind of looked at what's going on here. So again, the reason is that these things have been predicted and observed. So we were considered why we didn't get that. So we took a closer look at it. So what they argued is that they took the parameter from our paper. So you can see that the primary black hole masses are listed here. It's around 18 times million and all that. So they went on to calculate the gravitational wave luminosity using the quadrupolar formula. Just use the parameters from there. And they also said that they have provided an estimate for the orbital period and derivative, and I will say this is not our actual parameter. I'll come to that. So they computed these two and found out that they are inconsistent with each other. And they said there's a discrepancy between these two quantities at something like 4.3 sigma. They said that this can be explained if there are dark matter spikes giving dynamical friction and contributing to such gravitational, kind of flux which affect the dynamics. So, but the problem was that they didn't realize that these two quantities were sort of extracted, not measured. sort of derived parameter, and I clarify that. So we can actually do the same test for binary pulsar. You can see that these are the pulsar you actually measure. So you measure the eccentricity, projected semi-major axis, orbital period, advance of periastron, this is Einstein delay, and all that. These are all measured in the case of binary pulsar. And you can see that pulsar is just rotating, beam. And from that you can actually extract, thanks to GR, I'm essentially done. So, so because we have such independent measurements, but unfortunately for OJ287, we we can actually clearly show that these parameters are derived, so you cannot just plug them into that. And how did you derive? We just, because we were not interested in this, we just want to show them that it's very large compared to binary pulsar. So we just obtain it actually from the trajectory. So they should not have use anyway. So then we kind of corrected how we can actually do such a test properly. So that's essentially what we are trying. We actually showed that it's possible to do this test with OJ287. And in fact, we can say the following. We can take the ratio of the dynamical friction and the gravitational wave emission, ratio, and then we can say that the uncertainty in our measurements that actually can give you a constraint on the spike. That's essentially what we have done. The paper is being under construction, should be going soon. And so right now we are kind of looking at, well, can we actually do this in our template so that we can, eventually search with the PTA data. And Anish already talked about such dark matter density profiles for the background. So we thought it's a good way to kind of tell this. This is his paper. That's all. And just want to convince you that if you have individual supermassive binary black hole, these things will be fantastic, especially with the electromagnetic counterpart. You should be able to get the Hubble constant at the gigaparsec. Few measurements will be very accurate. Test of GR at epochs separated by thousands of years. That's very difficult to come by. Probing nonlinear aspects, lensing events, constraining ultralight dark matter because they have a periodic signal. Something, we are kind of working out because this can mimic an individual supermassive black hole. This is essentially the Kaplan's arguments. And then, of course, you have many, exploration on the anisotropy beyond the physics, paper like with Reggie, Bernardo, and others. Anyway, so I just want to again emphasize that GMRT is our baby, and we actually grateful for Govind Swarup, who came from United States to create this facility in India. And when he was kind of speculating on GMRT under construction, so in 91 he actually said that GMRT should be used to constrain stochastic gravitational wave. So PTA was sort of suggested in 89-ish, so that kind of a visionary, and he delivered GMRT, and we are using the benefits of that. And of course, when Balchandra initiated in PTA activities, of course, we are all influenced by Govind. And so our team is fairly young. You can see that, a few of us here. It will be great if some of the youngsters can join these efforts from a different perspective. We are pulsar astronomers or general relativity people, but this will have other implications. And I'm sure that many of you have association with NANO-Grav or EPTA, not from a pulsar or gravitational wave background, astrophysical. So that's it. Thank you very much, and I will be happy to take questions.
Thanks for finishing on time. We have time for questions.
Thanks. Nice talk. I want to know about the dark matter density you mentioned about.
Yes.
So how much is the density in the accretion disk? I mean, because that was not mentioned over there. So if I'm asking about, suppose I have dark matter spikes, and I ask the analyst how much mass I have.
Correct.
How that compares with the Aegean disk mass I have in the system.
So it doesn't really matter because the disk mass is not going to affect our orbital dynamics.
It will lose energy, right, in every passing because of interaction.
Yes, so that's kind of a friction on the trajectory, and that we actually argued in Loki's paper around 5 PN effects. So we don't really care.
That is true, but what I'm trying to understand is that suppose I said I have a disk and I also have a dark matter spikes.
Right.
Now, how would I know that how much loss of energy in every orbit is because of dark matter spikes and what component is coming from AGN disk?
So we can't, again, right now our measurements are not sensitive to dark matter spikes. That's what we are actually showing, because we can show that there is no inconsistency between the estimated and so-called measured values if you do this properly. So there is no sensitivity for the time being, but one can imagine that if you have actually a PTA signal, because the PTA signal, you need both the Earth term and the source, the pulsar term, and there are several orbits, right? This is around 10 plus orbits, but there will be several gravitational wave cycles, which depends on the orbital binary dynamics. If I have then kind of dark matter spikes giving the dynamical friction argument, I should be able to constrain it much better. That's the scenario. Am I clear what I'm trying to say?
I mean, yeah, but I think still will be a degeneracy with the AGN disk and dark matter.
AGN disk is not going to kind of constrain your orbital, the binary trajectory to the level the dynamical friction can. That's what we are seeing. Am I clear?
Yeah, I understand that. It's all depends on how much is the density in the AGN disk.
So we assume certain thin disk approximation and all that has to go in. I mean, if you crank up that, and we have very good constraints on that because we have seen the AGN.
So the volumetric luminosity of the AGN will give you a kind of a constraint mass.
Exactly.
So and
then you need to have kind of a curve which can affect the binary companion trajectory. That's kind of a high thing to ask for. That's what we felt.
Thank you.
Any questions?
Okay, so so my question is that so if there is some dark matter density spike, so that's basically the gravitational signature of dark matter.
Yes.
So so is there any way to probe any other interaction than gravity via these observations?
Yes, in principle, for example, in GR, it's very difficult to get a dipole radiation. But if you have scalar hairs and all that, Ted Jacobson talked about that sometimes back. So then you can create some sort of a dipole radiation, and that affect the binary evolution. I'm still in GR, but some, you have scalar fields which vary with time. Ted talked about it many years ago. It's a beautiful paper. Yeah. So those kind of things can actually, anything that affect the binary orbital dynamics should leave the signal on the PTA signal, and that's a possibility of constraining. That's that. Correct. So are you saying, yeah, so for example, in this Kaplan paper, they talk about it affecting the clock itself along with the PTA signal. That kind of argument, you're right? Is that what you're thinking about? Yeah. Okay. Oh yeah, so correct. So this spike business have been constrained because of the X-ray observation from the galactic center and all that. So some numbers, I don't have that in my mind, but they argue that those are not sensitive enough and all that. So, I've been hearing, I've seen like literature.
Yeah. We have time for one more question, and if there are no questions, let's thank the speaker again.
Thank you.